Hi folks, today we will be looking at the conduction of electricity by aqueous solutions of salts, acids and bases, and to explain how the results of similar types of investigations enable Arrhenius to formulate his theory about acids and bases. But first we need to understand what is a closed circuit and what is an open circuit, and to distinguish between conductors and insulators. Here we are seeing that we are having an electric circuit that is open. We have two electrodes here that are apart. There's no bridging between them. And if we were to take any substance and try to bridge these or to make a closed circuit, and it causes this light bulb here to light up, we will say that such a substance is a conductor. So you have four pieces of different metals here. We have a piece of nickel, and we'll just try to see whether or not nickel conducts electricity. It does. Piece of copper, it does. Piece of aluminum, it does. Piece of zinc, it does. So we can simply say that metals, these metals here, or generally speaking, all metals are good conductors of electricity. However, we'll now try to see whether or not other substances apart from metals are conductors of electricity. If you put it across this piece of wood here, we do not see the light bulb lighting up. Piece of glass, nothing happens. This piece of plastic here, nothing happens. And this piece of rubber here, nothing happens. But interestingly, we have a non-metal here in the form of graphite that does conduct electricity. Metals conduct electricity because of the presence of loosely held surface electrons around the atoms. And because of that, these electrons here can quickly respond when they are subjected to a difference in electric potential. For example, this conductometer here has two electrodes that are at a difference of electric potential of 120 volts. That is why when you put it across here, the electrons are able to quickly flow across from the cathode to the anode to complete the circuit, all because of the freely mobile electrons that are present in the metal. These are the types of substances which we call nonmetals here, are made up of atoms of elements that are held together by covalent bonds. And because of this type of bonding, the electrons are held in fixed places. As such, they are not free to move, and therefore they do not conduct electricity. Graphite here is an example of a nonmetal that conducts electricity. See, graphite is a form of carbon in which each atom has three of its outer orbitals sp2 hybridized, and the electrons within these orbitals are used to make covalent bonds to hold the other atoms of graphite together. However, there is one unhybridized p orbital here. See? So these are three sp2 hybridized orbitals with the single electron there, and these will form covalent bonds with other sp2 hybridized orbital to hold the carbon atoms together. But this one here is unhybridized, and this electron here is unbonded, and these are electrons here that are used to conduct electricity. I hope that was useful. Thank you so much. We shall now try to investigate the conductivity of aqueous salt solutions. But first of all, we will try to see if water conducts electricity or not. So water all by itself does not conduct electricity. Now we'll try to see if the salt by itself conducts electricity. The salt all by itself does not conduct electricity. So what we'll do now, we'll insert these two electrodes into there, and now we'll pour water into that and see what happens. All of a sudden you see it starts to conduct electricity. So water by itself will not conduct electricity. The salt all by itself will not conduct electricity. But if we dissolve the salt, we now see that the aqueous solution of sodium chloride conducts electricity. What we'll do now is this. We'll try to investigate whether or not all the aqueous salt solutions will conduct electricity, so and then make a general statement. So we'll introduce these electrodes into copper 2 sulfate. See, it does conduct electricity. Magnesium sulfate conducts electricity. Iron 3 nitrate conducts electricity. Zinc 2 chloride conducts electricity. So we can make a statement here, okay? That's because of the salt inside here. We can safely say that water does not conduct electricity by itself all alone. A solid or crystalline salts will not conduct electricity. But if you make a solution of any aqueous ionic compound, it will conduct electricity. But what is the explanation for that? So the next job that we have to do is to explain how an aqueous salt solution conducts electricity. We shall now endeavor to explain how aqueous salt solutions conduct electricity. What I have here, as can be recalled, is a conductometer. This conductometer has 2 electrodes which are at a difference of electric potential of 120 volts. One electrode is called the cathode and the other one is called the anode. Any substance that bridges or closes this circuit here, which is right now open, will allow electrons to flow from the cathode to the anode, and the circuit becomes complete or closed. So we can show you how a piece of metal is doing that. So as you've seen before, metals conduct electricity because they have loosely held electrons that allow the electrons to zip across from the cathode onto the anode. Okay? So that is how metals conduct electricity. Recall that water by itself was not able to conduct electricity, nor crystals of sodium chloride. However, when we pour water into the sodium chloride crystal, this is what happened. All of a sudden we see that the bulb started to light up, and that shows that this salt solution now is conducting electricity. Now recall that sodium chloride crystals have positively charged sodium ions and negatively charged chloride ions that are locked up inside this crystal by strong ionic bonds. However, it is believed now that when you add water to the crystal, the ions dissociate into sodium ions and chloride ions in billions, and that these ions now are freely mobile, and it is believed that there is a presence of those freely mobile ions within the salt solution that are responsible for the conduction of the electricity. Same thing will happen here if you put it inside a solution of copper 2 sulfate. So all salt solutions will conduct electricity. Okay, so we shall now try to explain how they conduct electricity. Okay, so this is sodium chloride here, solid. When it dissolves sodium chloride in water, it causes the dissociation of the sodium and chloride ions like this. So these are the ions that are present in sodium chloride in billions. Billions upon billions of these ions are present in any solution of a salt. When you do Avogadro's concept, you'll understand that more. So generally what I'm saying here is that any ionic compound XY, if dissolved in water, will give positive ions and negative ions, okay? Now, what we have here is a depiction of this conductometer here. It has a light bulb and it has these 2 electrodes here. This is the cathode and that is the anode. And these are connected to a power source here, and you have your light bulb in series there. For this light bulb to keep lighting up, or for there to be a continuous conduction of electricity, we need a constant flow of electrons into this cathode here and a continuous flow of electrons away from the anode. Now we want to show how these ions here are responsible for the conduction of the electricity. We want to show how they're responsible for electrons coming through this cathode here and electron moving away from this anode here. So this is the theory. The theory is this, that because these ions are freely mobile and this cathode is highly negative, has a high negative charge, and these guys here are positively charged, they're attracted to the cathode there. So when they go onto the cathode there, because the cathode is having lots of electrons, each of those positively charged ion that we call a cation now because they're going towards the cathode, will collect electrons from the cathode. If that cation is having only one positive charge, it will collect an electron. It becomes neutral and it deposits itself onto the cathode here. So if that was copper, 2 ions, it would have collected 2 electrons and deposited itself as a copper atom. If that process is allowed to go on for a long time, one would have seen that this cathode here become coated with a layer of copper. So these ions there, the cations, they're going there and collecting electrons from this cathode there. On the other side now, these negatively charged ions that we call anions, because they're negatively charged, they're attracted by the positively charged anode. So when they go there, what do? These ions here will give up their electron and become discharged, okay? In most cases, what will come off here are gases. For example, if that solution was copper 2 chloride, you would have gotten some copper atoms deposited there, and the chlorine ions would have given off 2 electrons and become a molecule of chlorine there, okay? So in most cases, what is deposited here is the metal atom, and what comes off here in most cases a gaseous element. So important thing to know is this. These ions are going to this cathode here and collecting electrons, and these ions are going there and giving up electrons. Because these are collecting electrons, it allows electrons to keep flowing down like this onto the cathode, okay? And because these are going and giving up the electrons, it causes the electrons, so the circuit now is complete. So it is believed that it is the presence of these cations and anions in the solution that are responsible for the conduction of electricity by salt solutions. I hope that was useful to you. All right, thank you for listening.
Yes.
Arrhenius went on further to investigate the conductivity by aqueous solutions of acids and bases. We have 3 sets of acids here and 3 sets of bases here. The first acid here is ethanoic acid, or what is called vinegar. This one is hydrochloric acid, and that one here is nitric acid. The bases that we have here are potassium hydroxide, sodium hydroxide, and ammonium hydroxide. So I want you to pay some attention to the intensity with which this light bulb lights up, okay? So we'll first of all put it into the solution of vinegar or ethanoic acid and observe the light bulb there. Here is hydrochloric acid. Note the difference between the intensity with which the light bulb lights up between ethanoic acid and hydrochloric acid. And this one here is nitric acid. So we can see that in these 2 cases, the light bulb lit up with a greater intensity than in this first case. Now we'll look at some bases now and see how they conduct electricity. We'll insert these electrodes into potassium hydroxide. It lights up brightly. Sodium hydroxide, again, similar to that. Ammonium hydroxide. See? We did not get the light bulb lighting up with that intensity as it did in these 2 here, okay? All right. What Arrhenius' reason was this, that since it is the ions that are responsible for the conduction of electricity in aqueous salt solutions, He reasoned that for there to be conduction in solutions of acids and bases, there must also be ions that are present inside these solutions. So when you look at the formulas of acids and bases, he was able to formulate his theory of acids and bases. And this is what he reasoned, or this is what he theorized. When you look at the formula here, hydrochloric acid, nitric acid, and chloric acid, he saw something that was common in all of these. He noticed that they all had hydrogen, the element hydrogen in their molecule. So he theorized that when these dissolve in water and they form ions, then they must have produced hydrogen ions. So his theory was that when an acid dissolves in water, it produces hydrogen ions, and it is the hydrogen ions that cause these things to be acidic. Similarly, when you look at the formulas for bases, he noticed that they have one radical in common, the OH radical. And he theorized now that if these conduct electricity, they must have produced ions, and the ion that is common with these is the OH ion. See that? So his theory is that when a base dissolves in water, or any base dissolves in water, they produce OH ions, and those are the ions that cause a solution to become basic. So that is how Arrhenius was able to formulate his theories. He looked at the conductivity of aqueous solution, why they conduct electricity, as because they produce ions. Solutions of acids and bases do the same thing, and therefore they must have produced ions too. But when you look at the formulas, they all have hydrogen ion in common for acids, and he's saying, okay, when these dissolve in water, they must have produced H+, and these are what's causing solution to become acid. And the same thing here for the bases, they have OH there, so when they dissolve in water, they must all produce that same thing there that's causing solution to become basic. Thank you. I want to take this opportunity to talk about strong acids and weak acids, and about strong bases and weak bases. But before I do that, I just want to repeat this demonstration here by inserting these electrodes into acetic acid, or ethanoic acid, or vinegar, and observe the intensity with the light bulb lights up. Okay? Now I'm going to put it into hydrochloric acid and see the difference. Who can say why the bulb lit up dimly here and very brightly there? Okay, go back to our understanding of why these things that are called electrolytes, by the way, those salt solutions and these acid-base solutions here, all called electrolytes. Why does the electrolyte conduct electricity? Because of the ions that are present inside. So the more ions something has, the greater will be the degree of conductivity, as in the case of hydrochloric acid, compared with ethanoic acid. So what can we say about the concentration of ions in hydrochloric acid compared to ethanoic acid? We can simply say that this has a higher concentration of ions than this one. That is why this is able to conduct electricity much more than this one. So why is that? The explanation for that is this. It is said that hydrochloric acid is a strong acid. So a strong acid, therefore, is said to ionize completely. These are molecules of hydrochloric acid. You can see they're molecules, right? Before they dissolve in water, they are molecules. But when we dissolve the acid in water, this is what happens. They ionize, okay? Hydrogen and chlorine ions separate from each other, right? The hydrogen separate away from there, okay? You can watch that, okay? Here, they're breaking apart, they ionize like that. It is said that for acids such as hydrochloric acid, there is 100% ionization. And because of that, that is why we have this high conductivity. So An acid that is said to be strong is one that ionizes completely. And of course, if it ionizes completely, it will have a high concentration of hydrogen ions, which causes acidity. Unlike that, the ethanoic acid wasn't able to ionize completely, and we call such an acid a weak acid. For example, if I had these molecules here, right? These are the molecules before they dissolve in water, right? So what happens when they dissolve in water, most of them will remain as molecules, but only a few of them will ionize to produce hydrogen ions and ethanoate ions. That is why there are few ions there to conduct electricity. And as such, we say such acids are weak acids, okay? So these are some figures here that I want to show you here, right? Look, if I had 1,000 molecules of hydrogen chloride, it's called hydrogen chloride before it ionizes, okay? If you had that and I have zero number of chloride and hydrogen ion initially, right? But the moment you dissolve that in water, look what happens. That's initial. Finally, you'll have zero number of molecules there, but all will be in the form of ions. So this is 100% ionized. That's why when you show it for a strong acid, you put an arrow going like that. In case of acetic acid or vinegar, if we start up 1,000 molecules, you'll have 0 and 0. Finally, look what happens. All of these will remain unionized, but only 13 ions of hydrogen and 13 acetate ion you're going to have there. That is said to be a weak acid. Same thing holds for bases, right? In this case, you're going to say ammonium hydroxide is a weak base. We can do that again. This is ammonium hydroxide. See that? Lit up dimly. Okay? Sodium hydroxide, very bright. This is sodium hydroxide we said to be the strong base, and ammonium hydroxide will be said to be a weak base. Okay, so the strong base and the strong acid ionize completely, 100% ionization, and a weak base and a weak acid only undergo partial ionization, and you will see like that. If you want to talk about sodium hydroxide now, you put AQ, you're going to put in one single arrow here to indicate that there is 100% ionization. Okay? All right, well, I hope that was able to let you understand the difference between strong acids and weak acids, and strong bases and weak bases. Thank you.